Good morning, students.
Good morning, sir.
So we'll start with the lecture now. Now today we'll study the magnetic field produced by Helmholtz coil and then magnetic field produced by solenoid. So first we'll take Helmholtz coil, which you have done the experiment. Now, first of all, what is the use of this Helmholtz coil? Now, Helmholtz coil is essentially used to produce very strong uniform magnetic field in a small region. Suppose in a very small region you want a very large field, then the Helmholtz coil is used. Now such high magnetic field, uniform but very strong magnetic field is required in a small region, especially in the scientific research. Now the Helmholtz coil consists of two coils. So you find here there are two coils. Say, coil number 1 and coil number 2. This is the coil number 1 and this is the coil number 2. Now these are two identical coils. So these are two identical coils. Identical coil means they have the same number of turns, the same radius, and the current also flows in the same sense. So here we have two coils. The radius is A here, this also radius A, and in the Helmholtz coil it is separated by distance 2b. Now what is the 2b? We will see that afterwards. And see here, suppose in the upper coil current flows in a clockwise direction, then in this lower coil also the current will flow in the same sense, both clockwise or both anti-clockwise. So because of this, move from here, move from there. Don't stand here. Either you go inside or out. See, the same when the magnetic this current flows in the same direction, say both clockwise or both anti-clockwise, then if you use a right hand thumb rule, then suppose in the both the coils it is clockwise, then if you use the right hand thumb rule, then the magnetic field at any point between the coil will be in the same direction. So magnetic field in the same direction means magnetic field will get added up. So that is the reason the current should flow in the same sense. So magnetic field due to both this coil should get added up. You can apply your right hand thumb rule and see. So if this is clockwise, this is clockwise, then the field will be here, in this case will be in upward direction for both. So they will get, the resultant magnetic field will get added up. Then see, these two coils should be such that the field at the point P, this point P has a distance Z. It is at the distance Z from the second coil. So 2B minus Z from the first coil. So current, so here at point P we want to find the magnetic field, and as I mentioned that the magnetic field should be as large as possible, because idea behind this Helmholtz coil is produce the magnetic field is very strong, so maximum possible field. So now here at a point is, if the point is at different distance, the Z is different, then field will be different. Now at some point it will be maximum. See, this magnetic field at the point P is a function of the Z. If Z is different, then field will be different. Then B is a function of the Z, Now we want to show that at some point the magnetic field is maximum. So at what point, at what distance it is maximum? So we use the calculus. In the calculus, that given function is maximum when first derivative is 0, then second derivative may be positive or negative. Accordingly, it will be optimum. So there is a theorem in the calculus which tells us. So what we will do is to show that it is a maximum at a certain distance. We will find the second derivative. So this value of the 2b will be chosen to make the second derivative of b vanish. Vanish means become 0 at some midpoint. So the idea behind here is at the midpoint between these two coils, the field produces as maximum as possible. And mathematically, to show that it is a maximum, we will find a second derivative and make it equal to 0. So this calculus we are going to use. Then we know the magnetic field due to the single coil. See this. B equal to mu naught Ni A square by 2A square plus Z square raised to 3 by 2. So we have like this. We have a coil like this. So radius is A. And if you draw the perpendicular to the plane of this coil passing to the center, that is called as axis. And at a distance, say at a distance here like this, at a distance Z from the center, the magnetic field is given as like this. B equal to mu naught Ni square divided by 2A square plus Z square raised to 3 by 2. So remember that mu naught is permeability, N is the total number of turns, I is the current through the coil. Now this is for a single coil. See what I mentioned here, or which we had derived last time, is a current due to single coil. A is the radius of the coil, and Z is the distance of that point from the center. Okay. So now we'll use this formula for these two coils. Say at the point P, say at this point, at the point P. So due to second coil, it is a distance Z. First coil, it is a distance 2B minus Z. So if you apply to the second coil, then Z is that Z. And if you apply to the first coil, then Z becomes 2B minus Z. Because in the original formula, Z is a distance from that point where you are measuring the field to the center. So if you use the second coil, then this is the distance. It is a Z. If you use the first coil, then this is the distance. Now this distance is nothing but 2B minus Z. Then to find the resultant field at the point P, as I have mentioned that these are identical coils sending the current, same value of the current, same radius, same number of turns, and sending the current in the same sense. So direction will be same, magnetic field direction will be same. So that's why to get the total field, we are adding it. Magnetic field to the second coil plus magnetic field to the first coil. Then for a second coil, same formula will apply. So here distance is Z. Then for the first coil, see first coil, that Z is 2B minus Z. So this Z is 2B minus Z, which is a distance from the center. Then we have to find out a second derivative of that magnetic field, and we will make it equal to 0. And when we make it equal to 0, then that condition will be satisfied, that at that point it will be maximum, field will be maximum. So now we have to simplify this. Before differentiating, we have to simplify this. So what we do here is mu naught Ni A square divided by 2. That is a common for both. So what is remaining there is 1 by Z square plus A square raised to 3 by 2. Then this 1 by 2B minus Z square plus A square raised to 3 by 2. Then take this in the numerator, become minus 3 by 2. This also in the numerator become raised to minus 3 by 2. So next what we will do is, we will differentiate this. We will differentiate this with respect to Z, because Z is a variable. See here, z is a variable. So this formula we have derived it previous slide. So now we differentiate this dBz by dz, because bz is a function of z. Z is a variable. So to differentiate this, mu naught ni square divided by 2 is a constant. It comes as a constant multiple. Now differentiate this term. Differentiate this term minus 3 by 2 comes as a multiple. Then see, you are differentiating the bracket. So minus 3 by 2 comes as a multiple. Then power reduces by 1. Minus 3 by 2 minus 1, that is minus 5 by 2 into derivative of what is there inside the bracket. The derivative of this, what is there inside the bracket, derivative of z square is 2z, because with respect to z, a is a constant, so that is 0. So we have differentiated the first term. Then we will differentiate the second term. So minus 3 by 2 comes as a multiple. Then power reduces by 1, that is minus 3 by 2 become minus 5 by 2. When you differentiate inside, see, derivative of a square is 0. Derivative of 2b minus z square is 2 into 2b minus z into derivative of still what is there inside. So derivative of this 2b minus z is 2b is 0 minus z is minus 1. So this is what we get. And then this minus 3, we take it out. These 2 cancels. Here we cancel these 2. And minus 3 we take it out. So what remains in the first term is this z, and this z into z square plus a square raised to minus 5 by 2. Then what remains here is this minus sign is there. See, this minus sign is there. So minus sign. Then 2b minus z into 2b minus z square plus a square raised to minus 5 by 2. This term we get. Then again we differentiate. You differentiate this again with respect to z. Then here this term is constant, comes as a constant multiple. Then derivative of this z into z square plus a square raised to minus 5 by 2. So derivative of the product. So derivative of first term into second term plus first term into derivative of the second term. Then here derivative of z is 1. So derivative of first term, that is z, is 1. Then second term repeats. Plus the first term, which is z, and derivative of the second term, which is z square plus a square raised to minus 5 by 2. So minus 5 by 2 comes as a multiple. And here the power reduces by 1. 5 by 2 minus 5 by 2 minus 1 is minus 7 by 2 into derivative of what is there inside, which is 2z. So here these first 2 terms is a derivative of this part, z into z square plus a square raised to minus 5 by 2. In same way, you differentiate this second term. This term you have to differentiate. Then here again same way, minus sign is there. Then derivative of first term, 2b minus z. Derivative of 2b is constant, minus z is minus 1. So we have differentiate this. Minus is there, and what is minus 1. And into second term, 2b minus z is square raised to 2 raised to minus 5 by 2. So this is a multiple, it comes as a multiple. Then the first term minus 2b minus z into derivative of second term. So minus 5 by 2 comes as a multiple, power reduced by 1, that is minus 7 by 2. And derivative of what is there inside is this 2 comes as a multiple, 2 into 2b minus z, derivative of a square is 0, into derivative of what is there inside, that is minus 1. So then here also what we do is this, we write this z square plus a square raised to minus 5 by 2. It will come down as plus 5 by 2. Then minus 5z square, see this z and this z, z square. 2 cancels. So minus 5 z square, and this z square plus a square raised to minus 7 by 2 will come down in the denominator s plus 7 by 2. Same way, the third term, third term, this minus minus 1, say this minus minus plus, minus minus plus, okay, so it becomes plus, and this second term goes inside and denominator s plus 5 by 2, we get this. Then here also, this 2 cancels, then then this minus 5 2b minus z, that remains in the numerator, and this part minus 7 by 2 comes down as plus 7 by 2. So you get this second derivative of bz. Then this, say, now what is said earlier that it should be maximum at the midpoint. So if you go back to the earlier slide, so midpoint. So here the midpoint means the midpoint is the total distance 2b. So midpoint is at b. So we want it maximum at the midpoint. So value of z should be equal to b. So what we do is we find its value. So we will find its value of second derivative at z equal to b. That means at midpoint. So we put z equal to b in that earlier equation. We put in the equation which we have derived, this equation. In this equation, we'll put z equal to b. Wherever z is there, we'll put equal to b. And when you put it, you get it like this. We get like this, z equal to b. Here b square, here b square. This is 2b and 2b. And then we'll simplify this. So we simplify all this term, find the LCM of that, and when you simplify, what you get in the numerator is, see, this is minus 3 mu naught n I a square and minus 4 b square plus a square divided by b square plus a square raised to 7 by 2. This is what you will get. This is second derivative. And to be maximum, second derivative has to be equal to 0. And that is from the calculus. So maximum when the second derivative is 0. Now for this side to be equal to c, in order that this is equal to 0, what is possible is this numerator has to be equal to 0. See, this minus 3 mu naught n I a square cannot be equal to 0. Because mu naught has its own value, number of turns are there, current has to flow, radius has to be there. So this term cannot be equal to 0. So in order that this full term is equal to 0, when the numerator equal to 0. So we put minus 4b square plus a square equal to 0, that gives a equal to 2b. So that means the coil separation should be equal to the radius. So the field at that midpoint between the two coils is 0 when the coil is separated by distance equal to the radius. And this is what we have used for the practicals. See, we have used for the practicals when the coil separation is equal to the radius. See, we are keeping the two coils separated by distance equal to radius. In fact, from that magnetometer, center of the magnetometer, we are keeping a distance up to the coil equal to half the radius. The reason for that is, in such case, the field is a maximum. So the maximum field is at z equal to b. So then we calculate that at z equal to b, what is that field? So we take the formula for b. This is the formula for b which we have found it in the first slide. Equation 1, we put z equal to b. So we put z equal to b. And when you put z equal to b here and z equal to b here, and when you simplify this, say further we use, say this a equal to 2b. So the distance between the two coil equal to the radius, that also we use. And when you simplify, you get the value of the magnetic field at that point is mu naught Ni by A, 8 divided by 5 raised to 3 by 2. So that will be in fact when you keep the two coils, two identical coil. Identical coil means they have the same radius, they have the same radius, same number of turns, the current is flowing in the same sense, same current flows in the same sense, so the field will get added up. Then the magnetic field at this at the point will be equal to this. Actually, you can calculate that mu naught Ni. You know the number of turns. In both the coils, we keep the same number of turns, current, radius, and 8 by 5 raised to 3 by 2. In fact, you can calculate that magnetic field. So you can design the Helmholtz coil to produce a one particular field, whatever which you require. If you want to have a larger field, increase the number of turns. If you increase the number of turns, then what will happen is the field will be larger. If you increase the current, the field will be larger. If you decrease the radius, then field will be larger. That is how in actual practice it is done. Helmholtz coil, suppose you require a certain value of the magnetic field, then we adjust number of turns, current, and the radius. Okay, so this is what you have done in the practical. In practicals, what you have done is, under condition that the distance between the two coils is equal to the radius, we have shown with the help of the graph that it is a maximum at a midpoint, highest value. So sort of a peak was obtained at the center. So this is what is called as a Helmholtz coil. Okay, then next we take is a solenoid. See, we take up a solenoid. Now actually you already studied the solenoid in your 12th standard. Helmholtz coil you have not studied. The straight wire you have studied. Then the coil you have studied. Straight wire, magnetic field with straight wire you have studied in your 12th standard. Then the magnetic field due to the this coil you have studied. And magnetic field of the solenoid also you have found it. But we find here in more detail. Okay. So basically what is a solenoid? Solenoid is essentially, say, what is called as a straight solenoid. I am not speaking about the toroid. There are two types of solenoid. One is a straight solenoid, or is simply called as a solenoid. Other is a toroid. The straight solenoid is just like a spring. All of you have seen the spring. It is like a spring. Spring means what? Wires are turned along the length. See, this coil means wires are coiled over and over again like this. That is the coil. If the wires are coiled along the line like this, then it is called as a solenoid. There is a difference between the solenoid and the coil. Coil means all the turns are in the same region, whereas in the solenoid they are along the length. It is just like you pile the coils one above the other. There is a solenoid. Okay. So now I have drawn here, see what is drawn in this diagram is the vertical cross section of that solenoid, which is a spring. So through the spring, when the current flows, then it is called as the solenoid. And this is what is called, see, in the biology you might have come across horizontal cross section and vertical cross section. Okay. Now this is what is called as a vertical cross section. So I have shown here dots like this. See, these are dots. So from the side you see those wire is there like this. A coil is there. So from this side you will see the dots. You will see the upper dot and the lower dot. So actually what happens is this coil is going inside, coming out from here, then going inside here, coming out. Those coils of the solenoid are perpendicular to the page. Then let us say that the total number of turns of the solenoid is n. See, there are n turns. See, 1, 2, see the first turn, second turn, third turn. So there are capital N turns. Radius of this is A. Radius of this solenoid is A. Not the radius of the wire. It is the radius of that turn of the solenoid is A. Then total length is L. So this is the total length. Total length is L. Now what we will do here is, we will find a magnetic field at the point P at a distance Z0 from one of the end. See, we will find it at distance Z0 from one of the end. So this is the point P, is the distance Z0. This is the distance Z0. So now what we will do here is, say, now we know the magnetic field at the axis of some coil. So these are the point, these are piles of the coil, and this point P is the axis of that coil. But there are many coils here. Okay, so we know the formula for that magnetic field on the axis of the coil. So we'll use that. So what we do is, that full solenoid you divide into small sections. We call it as the element. Element means what? That section, the width is tending to 0. So we'll see it. See, in fact, what happened is, in actual solenoid, these turns are very closely spaced. So we'll take some element of that solenoid. Element means a very small part of the solenoid, a very small horizontal cross section of that solenoid of the length dz. Length of the element which we take is dz. Dz is a coil. See, the width of that coil is dz. See, this is the width. Width of this coil is dz. So in this dz there are many turns. So we consider this element of the solenoid as a coil. See, element means what? A small part of the solenoid as a coil. Width is dz. Now here the total number of turns are capital N. See, total number of turns are capital N. See, total number of turns of the solenoid is capital N. If you divide this N, see, if you divide this N by total length, what you will get is number of turns per unit length. See, the total number of turns is N, so length of the solenoid is L. So if you divide the total number of turns divided by length, then you will get a number of turns per unit length. But what is the length here? dz. So how many turns are there? You multiply that by dz. So N by L, see, N by L is the number of turns per unit length. If you multiply by length, you will get a number of turns over this element. So that is what we get. So now we have a coil which is the element of this solenoid, which has the number of turns equal to N dz by L. So N by L is the number of turns per unit length of that solenoid, and if you multiply by that length dz, you will get how many turns are there in this element. Then we have this formula, axial field of the coil, which we have derived last time, mu naught Ni A square divided by 2 A square plus Z square raised to 3 by 2. We rearrange it, mu naught by 2 N I A square Z square plus A square raised to 3 by 2. Z is the distance of that point from the center of that coil. So here it is the element. So now what we will do is, to that element we will use this formula. To this element of the solenoid means coil, we will use this formula, and then we will integrate. Integrate means add the magnetic field due to each and every element from this end to the other end. That's what we are going. So to find a magnetic field at a point P due to full solenoid, that means what you have to do is, the magnetic field you have to add due to each and every element which we considered from this end to other end, and we integrate it from 0 to L. So this end is at 0, other end is at L, 0 to L. Integrate. But what is the magnetic field of that element? We use it here. See, we have mu naught by 2. So how many turns are there? See, here what comes is N. But N for each coil is N dz by L. That for the number of turns of this element of the solenoid is N dz by L. Then I A square divided by, now this, say, this point P, what is at what distance it is from that element? This distance. See, in actual formula here, The z is the distance of that point where you are finding the magnetic field on the axis from center. So this point P is here and center of that element is here. So this distance turns out to be z naught minus z. See z naught, this is z, this distance is z naught minus, because this is a distance z naught and this is distance z. So z naught minus z. So that's why it is z naught minus z. So we have now here we have written that, and we take the constant outside, mu naught ni by L a square by 2. 0 to L, z is a variable. See this, the point P can be anywhere. Point P can be anywhere on the axis. So what is variable is, element can be anywhere. Element can be anywhere. Element can be here or at this end. So what is variable is, z is a variable. So it remains inside the integral. Now we have to evaluate this integral. We have to evaluate it. Okay, so z is variable. So in order to evaluate it, see here, this is not a standard integral. Integral of 1 by z naught minus z square plus z square raised to 3 by 2 is not standard integral. So what we will do here is, we will try to put here the trigonometric quantities and then we will integrate it. So now in the diagram, see in this diagram, you take a cot of theta. This is theta. Cot of theta. What is cot of theta? Adjacent side. Tan of theta is opposite side divided by adjacent side. So cot of theta is adjacent. This is the adjacent side. Adjacent side is z naught minus z. This is the adjacent side. And opposite side is a. See this opposite side divided by adjacent. So opposite side is a. Adjacent side is z naught minus z. And cot of this angle is adjacent side is z naught minus z divided by a. We simplify this. Z naught minus z equal to a cot theta. Now we require what is dz. So differentiate this. Z naught is constant. See that this point P is a fixed distance from the end. So z naught is constant. So the derivative of constant is 0. Then we write dz by d theta. So minus z is minus dz. Then a is constant. Derivative of cot theta is minus cosec square theta. So derivative of tan theta is sec square theta. So derivative of cot theta is minus sign will be there, and cosec square theta. So into d theta. So actually what you have done here is we have differentiated z with respect to d theta. So you get it like this. So minus minus cancels and dz equal to a cosec square theta d theta. So we have found out what is dz. What is dz we have found out, and what is z naught minus z also we have found out. Z naught minus z is a cot theta. So we have to substitute here. Z naught minus z as cot theta. This we will substitute, and we will substitute this dz a cosec square theta, and then we will integrate it. Now beside this, we want to find out what is the limit. Limit will change now. Now this limit 0 to a was for z. Now what is the angle theta? Say, now if you take this at this end, say 0, here L equal to 0, at this end L equal to L. So L equal to 0, that angle theta, see this, when you take the element here, when you take this element at this point, then angle is a theta 1. That's what I will write. And when you take this element here at this, see what is done here is, this element is taken here. What is the angle subtended? Theta 1. You take this element here. What is the angle subtended here? Theta 2. So instead of from 0 to L, it will become theta 1 to theta 2. So when the z is equal to 0, the angle subtended is theta 1. When z equal to L, then angle is theta 2. So that is what we have written here. See, this we have found in the previous slide, bz, then z naught minus z, and dz, and limit we have found out. So we substitute here. In the first, this equation we substitute. Mu naught ni by L a square by 2 is there. Instead of 0 to L, theta 1 by theta 2. And dz is a cosec square theta d theta. And z naught minus z is a cot theta. So a cot theta square plus a square is to 3 by 2. Then this square this a square cot square of theta plus 1. But cot square theta plus 1 is nothing but cosec square theta. See, this cot square theta, 1 plus cot square theta is cosec, just like 1 plus tan square theta equal to sec square theta. 1 plus cot square theta equal to cosec square theta. So cosec square raised to 3 by 2. So cosec cube you will get here. So this, what is here is, now this one here is cosec square raised to 3 by 2. Raised to 3 by 2 means 2 and 2 cancel. What you will get is 3 here. Then this cosec square will cancel with this. What will remain is, now this here, that a and a cube, that is a square. So this a and this a cube will cancel, and only one cosec square will remain. Cosec will remain here. So cosec square by cosec cube. So cosec will get, and 1 upon cosec is sin theta. And now it is very simple to integrate this. Integral of sin theta is minus cos theta. Lower limit is theta 1, upper limit is theta 2. Substitute the this upper limit minus substitute the lower limit, but minus sign is there. Minus sign is there. So here I have a minus of cos theta 2 minus cos theta 1. That is cos theta 1 plus cos theta 2. So this is the magnetic field at any point inside. At any point inside, the magnetic field is this equation. Magnetic field is this: mu naught Ni by L half cos theta 1 minus cos theta 2. So this is at anywhere in between. Then we take some special case. If the solenoid is very long, say this we have derived. This we have derived. In general, we have derived the magnetic field at any point inside the solenoid is mu naught Ni by L half cos theta 1 minus cos theta 2. Now we take a special case. Suppose solenoid is infinitely long, very very long solenoid. Normally what happens is, the radius of the solenoid is very small as compared to large is very large. Length is very large as compared to the diameter. Okay, so such we call it as infinitely long solenoid. Then here what happened is, if it extends on this side, see if it extends, this is what happens to theta 1. If this end goes further and further, this theta 1 will become less and less, but what is the minimum value you can take is 0. It will become 0. Then here, this side goes to infinity, so angle theta 2 will go on increasing. What maximum value it will become is 180 degrees. Suppose if we extend this solenoid on both the sides, so theta 1 in limiting case it will become 0, because if we take this element further and further, theta 1 becomes smaller and smaller, but minimum value it will take is 0 at very large distance. Now if you take this element away and away, then what will happen is this angle will become bigger and bigger, but what maximum value it can take is 180 degrees. So limit here is going from 0 to 180. 0 to 180. So theta 1 is 0, theta 2 is pi. So when you substitute in this formula when you substitute cos of 0 and cos of pi, cos of 0 is 1, cos of pi is minus 1, minus minus plus. So 1 plus 1, 2. So this will cancel with this. And what you will get is mu naught Ni by L. And N by L, number of turns per unit length, is mu naught Ni. And this is what you have found in the 12th standard. You have derived it. But you have not used the Biot-Savart's law. You have used some other method. That also we will use later on. But this magnetic field is inside. Magnetic field is inside the solenoid. Well inside the solenoid. Okay. Then one more thing we'll see is, what is the magnetic field at the end? Magnetic field at this point. Suppose if we shift this point P, you can shift this point P here. Suppose if we shift the point P here, you take infinitely long solenoid. If you shift the point P here, then theta 1 will be equal to 0. Theta 1 will become equal to 0. And theta 2, see, this theta 2, point P is here. So theta 2 will be equal to 90 degrees. And theta 1, see this theta 1. So from here, if it is infinitely long solenoid, this will become very small, tending to 0. So theta 1 is 0 and theta 2 is pi by 2. So we have cos of 0 minus cos of pi by 2. Cos of 0 is 1, cos of pi by 2 is 0. And when you simplify, what do you get? Mu naught Ni by 2. So at the ends, so this formula which you have not derived in your lower class, you have found only magnetic field inside. So and it is not mu naught Ni, it is mu naught Ni by 2. Either at this point or at this point, the magnetic field will be mu naught Ni by 2. Then outside the solenoid, you can draw the these magnetic field diagrams and see that the magnetic field is nearly negligible outside the solenoid. Now along this axis, field will be there. It's just like a bar magnet. So solenoid is behaving like a bar magnet, exactly like a bar magnet. So solenoid is behaving like a bar magnet. So at the ends, the magnetic field will become less and less as one goes away. At the end, it is mu naught Ni by 2, and inside it is mu naught Ni. So this is the expression for the magnetic field due to the solenoid. So what we consider today is a Helmholtz coil, the magnetic field produced by Helmholtz coil and the solenoid. So with this, I'll stop here and continue tomorrow. Thank you very much.